All right, welcome everyone. Thanks for waking up so early after this tiring conference. So today we have a excellent line of speakers for the workshop. So the workshop's focus is mostly on coming up with very small models that can be fit onto your tiniest of devices or when your prediction has to be on budget. The first speaker that we have is Forrest Iandola. Forrest is working at Deep Scale, and they are coming up with these deep learning models for embedded devices. And after that, we'll have Shiv from Amazon, who is working on Alexa. So because this is an area which is up and coming, and we have lots of exciting problems in this area. So it's not that we have already well-defined set of problems. We are all struggling with this definition of problems, what the correct questions to ask here, etc., etc. So please, let's keep it very informal, more discussion-oriented. So each of our invited talk is for about 35 minutes, and we have asked our speakers to just make the talk for about 25-26 minutes, and the remaining time we want to spend on questions and answers and just discussions. So let's keep it that way. And in the evening we have a panel about which, the goal of the panel is to just discuss what are the current directions that people are thinking about, what are the important problems, how we can take these things to pretty large scale and have sort of very impactful systems and algorithms. So without further ado, let me invite Forrest and get started.
So my name is Forrest Iandola, and I'm going to be talking about small deep neural networks, their advantages and their design. This talk is less of a research talk. It's a little bit more like a tutorial format, I would say. So we're going to be not so much beating the drum for new research that we've done. It's more, I'd like to kind of share some of the learnings we've had over the past couple of years in developing small neural nets. So I'll first start with computer vision. After 40-some years of research, finally works pretty well. So now, how do we productize that and deploy it? We'll find that making neural nets smaller is one of the key factors in how we make that happen. We'll talk about some advantages of small neural nets, why it's useful for neural nets to be smaller, especially in sort of embedded and in the wild gadget type of applications. And then finally, I'll go through some design principles that we and others in the community have found are quite useful for developing smaller neural networks. So computer vision, after a long history, finally works quite well. So what I'm showing here is a plot that many of you have probably seen before, which is the ImageNet error and how it's improved in the last 5 or 6 years. So from 2010 to 2016, it's gone from about 30% to about 3% of the best models that have been reported in the literature. So an order of magnitude improvement. And we've seen similar types of improvements elsewhere in computer vision. For example, in semantic segmentation, object detection, 3D reconstruction, and so on. And outside of vision as well, in audio and text and other areas, we've seen huge improvements due in part to new machine learning algorithms and particularly deep neural networks, but also in as a result of better and better neural networks and new innovations in neural nets. It's not just neural net or not, it's consistent, quick progress on improving neural nets and their accuracy. I have plenty of seats up front, too. So computer vision finally works. Now, what are the venues for deploying this to create value for real products? So from my perspective, I see kind of 2 big buckets of where vision is useful. So there's first the data center applications, of which there are tons. So a couple of examples would be social media analysis in the cloud, web indexing, government intelligence, things that, while being important, don't necessarily require real-time results from any of these. A lot of this can be done batched and offline. The other area I would say is what we might generally call gadgets, so stuff that's not purely in the cloud, so self-driving cars, smartphones, drones, and other real hardware that's outside the data center. And in the sort of server space, I think a ton has already happened. There are many products from Google and Microsoft and Amazon and others have especially a big server presence and are already creating value for lots of people. I think in gadgets, we're just getting warmed up right now. So in terms of the requirements for what do you need in order to be successful in using vision in these applications, so in data center land, I would say it's not usually safety critical. You're not usually manipulating physical hardware that could hurt somebody. Low power is definitely useful, but it's not necessarily a key enabling technology to get off the ground. And then real time also tends to be useful, but again, there's a lot you can do in batch processing on data center as well with vision and learning. So gadgets are a little bit different. So in gadget land, except smartphones, usually safety critical. So we're talking about things like multiple tons of weight of vehicles driving around on the road, drones that could crash into all kinds of things. So not crashing into stuff is super important, and so it's safety critical. Low power is really important, and the reasons for that vary depending on the application. So on smartphones and drones, it's often especially an issue of battery life. In things like self-driving cars, often it's more an issue of smaller processors that can work under passive cooling, often can be more reliable and last for the lifetime of a car. And then real time in most gadget applications is super important. So in terms of smartphones, no one likes to be kept waiting. And in terms of robots and drones and cars, it's all got to respond in real time because it's interacting with the environment. So a lot of what we're going to talk about in this talk, I think, will be especially useful for gadgets, but hopefully we'll add some value on the data center side as well. So to kind of restate that, so what's the right neural network for use in gadgets? So I think some of the key desirable properties are sufficiently high accuracy, which is defined with respect to exactly what problem you're trying to solve. Low computational complexity, ideally such that you can run it in real time on a fairly modestly sized embedded processor. Low energy usage for the reasons I mentioned before, for battery life, for lower cost, smaller chips, and longevity. And then finally, one I haven't mentioned yet, and I think the one that's just starting to get warmed up is small model size, which, so let's talk about why small model size in particular is quite important. So why small deep neural nets? So there are lots of reasons. I'll discuss three of them at some level of detail here. So first of all, small deep neural nets, we found in our research, and others have found the same thing, that they train faster on large-scale hardware. So the amount of gradient updates you have to transmit when doing data parallel distributed training is equivalent to how many model parameters you have in your neural net. And so the fewer parameters you have, i.e. the smaller model you have, the more hardware you can throw at it, assuming the same amount of computation but fewer parameters, and the faster you can finish the training. Also, on embedded processors, memory or computation is at a premium, but memory is at a huge premium. So small embedded processors often have slower memory and less of it. And so the more of the model, ideally all of the model, you can fit on the chip itself without interacting with the memory, the more successful you'll often be in deploying it on an embedded tiny little processor. And then finally, I think most applications where we care about all these different things, about efficiency, about accuracy, and so forth, there are tons of innovations that will happen on the neural net side and developing better nets. There will also be lots of information we gather from the devices themselves, potentially. And so all of this culminates in to keep improving the devices after they're deployed, we'd like to be able to over-the-air update them. In other words, ship new model parameters to them. And so the smaller the model is, the less communication you have to do for that. So I'll go through each of these in just a touch more detail. So, sorry, slides format changed a little bit. I borrowed these from Kurt Koitzer. These are slides we've had for some time, but they should illustrate the point well. So this work is an extension of our CVPR 2016 paper on FireCafe. So what we reported in that paper was on 128 GPUs, we could speed up training by 47x by using some all-reduce-based data parallel communication. And somewhat disappointingly, when we tried 256 GPUs on the Titan supercomputer, we only got about a 60x speed up total over single machine training or single GPU training with GoogleNet. And the reason was most of the time was going into communicating between machines. So we designed this net called FireNet, which is similar to SqueezeNet in architecture with a few different hyperparameters than SqueezeNet. And it's substantially smaller than GoogleNet, so 13 megs instead of 53 megs. And it has similar accuracy, and on 256 GPUs, we got it to be 145 times faster than single machine training. And I think it took around, if I recall, 3 hours to train to GoogleNet level accuracy. This is in 2015 with like 2 or 3 generation old GPUs compared to what we have now. So the smaller model size with similar compute footprint led to faster, more distributed training. So another advantage of smaller models is their amenability to going on embedded hardware. So as we mentioned before, the energy efficiency in embedded hardware land is really critical. And if you compare the amount of energy used to do a computation, so an add or multiply on a floating point number, to the amount of energy you need to move that in and out of the DRAM off chip, the memory hierarchy off chip, it's like a 100x difference. It's 100x more expensive to move the data on and off chip than it is to manipulate the data on chip. And so the less we can be dependent on off-chip memory, the more efficient we can do things in embedded hardware. And that's one reason why smaller models have the advantage on embedded hardware. And then finally, over-the-air updates, or we might call it continuously updating models. So anytime a gadget in the wild discovers an anomaly that may require retraining or sending that model to a human to take a look and do some quality assurance and then add that to the training set, continue the model training, and then ship a new model, the smaller the model is, the cheaper this is to do. And in some cases, like if you look at how Tesla does their over-the-air updates in their cars, you connect to Wi-Fi first. And so shipping a 250 megabyte model over Wi-Fi, while not free, is sort of reasonable. But if you look at the mainstream automakers like General Motors, they don't assume that you're taking your car into your garage and plugging it into the wall every night and being near Wi-Fi. So a lot of people, park on the street. And so GM has architected their client car I should call it car cloud interaction system over, I believe, 4G in their OnStar system. And so that OnStar system, even without doing deep neural net stuff, just doing normal telematics communication to the cloud, based on talking to some people who work in the telematics space, about 60 to 70% of GM's cost of running the OnStar program goes directly to telecom companies to pay for that 4G data. So imagine how that's going to blow out once we start transmitting new neural nets to cars. So the smaller the model is, the cheaper this whole over-the-air update business will be. So that's the motivation on why small neural networks are really important. Now I'm going to talk about a couple of key advances in the small neural net space over the last year and a half or so. And especially in the past few months, there's been an explosion of research in this area, so I can't possibly cover it all. But I'll talk about SqueezeNet and about mobile nets, which are two interesting results in this space. So SqueezeNet is a model that a few colleagues and I invented about a year and a half ago now, or published about a year and a half ago now. And so it's comprised primarily of these fire modules, as we call them, which are sort of like a simplified inception modules. They have one filter bank of 1x1 filters, followed by a mix of 1x1 and 3x3 filters. So what we call the squeeze conv layer, some people call that a bottleneck now. So it has fewer filters than the previous layer typically. And then the expand layer with a mix of 1x1s and 3x3s, we designed it that way so we could play with how many 1x1s and how many 3x3s in a layer and what trade-offs to do there. So I'll get into more of the nuts and bolts of convolutions and designing their dimensions later on in the talk. But the main result from the SqueezeNet work was, so up to that point, people who wanted to make smaller models, one of the key things they did, and still do to good effect, is what they call model compression. So here are a few model compression techniques applied to AlexNet. So that takes us from 240 megabytes to just about 7 megabytes using a technique called deep compression, which deletes some of the parameters and then quantizes the remaining parameters. So that's a 35x smaller model with the same accuracy. So that's quite impressive. But when we realized how SqueezeNet compared, so SqueezeNet with no model compression at all is 50 times smaller than AlexNet with the same accuracy level. So that was quite exciting. And we actually teamed up with Song Han and some of his colleagues at Stanford and NVIDIA who did the deep compression work and applied deep compression to SqueezeNet and found that we could get another factor of 10 shaved off. So that's about a 510 times smaller model than AlexNet with the same accuracy level. So you might ask why AlexNet. So the AlexNet was a model that was particularly popular in the model compression community, so we thought we would just compare directly to that. And so I think this was one of a few papers that really got people revved up about making smaller models, and there's been an explosion of work since then. One of the more interesting ones is called MobileNets from Andrew Howard and some of the folks in Google Research. And one of the key ideas they've sort of popularized is what we might call depth-wise separable convolution filters. And so the idea of having convolution filters that only apply to a subset of the channels in a neural net, even AlexNet did some of that with I think, groups set to 2 in group convolutions. But what's cool about this is they actually just have 3 by 3 by 1 channel filters and a unique filter for each channel. And so this saves hugely on the number of filters in the 3 by 3 convolution layers. And I'll get into more of this later. And so the key result, I would say, is, well, number one, I really like that this paper actually doesn't just report one model, but it reports a variety of versions of the model that have different trade-offs in terms of accuracy, model size, and speed. And I think that's really important to share that intuition on what's the range of things that we found, not just what's the single model that we thought was most impressive. So in the context of SqueezeNet, so SqueezeNet had about 57 point something % top 1 accuracy on ImageNet. There's a version of MobileNets here that I have that green arrow next to that is about 5 percentage points, or a little more than 5 percentage points, more accurate than that, while using about the same quantity of parameters. So in absolute terms, this has advanced the state of the art over SqueezeNet, and plus it's provided a more rich range of models with different trade-offs in this space. So those are a couple of compelling results, MobileNets and SqueezeNet, and of course there are many other exciting ones as well. Let me now move on to, okay, so small models are important. A lot has been done in small models. So how do you create your own small neural net? What are the ingredients? How do you go about it? So before I get into that, let me just briefly talk about what I call the anatomy of a convolution layer. So a convolution layer basically has, the black thing there is the input data. So if this is the first layer in the neural net, that would be the image, for example, with 3 channels. If it's a later layer, it would be the activations from the previous layer, temporary variables the previous layer generated. And so it has a height and a width and a number of channels. And number of channels is defined by how many filters you had in the previous layer, typically. And then there's a filter, so that green thing is a filter, so it's got a height and a width and a number of channels. And then typically there are multiple filters, which the number of filters is something you as an experimenter would set or define. And then there's often a batch size, which allows you to concurrently compute more than one image if you'd like to. So a lot of you probably already know this. The reason I'm going into it is because we're going to be manipulating some of these dimensions in the following discussion. So I'm going to go through now 7 different techniques that you can apply individually or all together, if you'd like, for coming up with smaller models. So the first one is replacing fully connected layers with convolutions. So in models like AlexNet and BGG, most of the parameters are in fully connected layers. So for example, the FC7 layer of AlexNet has 4,096 input channels and 4,096 filters, so that's 67 megabytes of parameters, which is about 13 SqueezeNets worth of parameters in one layer. So I'm not saying that fully connected layers are bad by any means. Rather, what I'm saying is, in these particular models, the designers of those models decided to have lots of filters and lots of channels in those FC layers, so it just turns out they have lots of parameters as a result. And so what we've found in our experiments is often you can substitute those FC layers with more convolutions, have fewer filters and fewer channels in those convolutions, but then have a larger activation grid. FC layers are basically convolutions with a 1-by-1 activation grid, so you can make that bigger and often preserve accuracy with about the same compute footprint and lower number of parameters, which gives you all those benefits of small models that we talked about before. Another technique, and this is one that we relied on heavily in SqueezeNet, is replacing what we call kernel reduction, so reducing the height and width of some of the filters in a neural net model. So in particular, a flavor of this that I want to highlight is replacing 3x3 filters with 1x1 filters. And some people get confused. What's a 1x1 convolution filter? Wouldn't that be a scalar number or something? Well, what we're actually looking at is 1 by 1 by number of channels. So it's like a vector that gets multiplied by all the channels at each xy location in the activations. And so these 1 by 1 filters can't really see outside of 1 pixel radius, except just using the receptive field from previous layers, but they retain the ability to combine and reorganize information across channels, which turns out to be quite powerful. And so when we were hunting for the SqueezeNet model, doing design space exploration, exploring a variety of models and defining them and training them, we found that for one particular SqueezeNet-like model, we started out with certain layers had all 3x3 filters. When we replaced half the 3x3 filters with 1x1s, we got the same accuracy, but saved a significant number of parameters. Of course, a 3x3 has 9x more parameters than a 1x1, so that's very important. And then I just want to highlight, when looking around, searching the design space and trying different models, there's often a point where adding more parameters in some dimension doesn't actually lead to any more accuracy. And so I call it a saturation point. So the neural net design space is infinitely large, but when you can search for what's the point where if I add more parameters in this particular dimension of the net, it doesn't help accuracy, it just wastes more compute and model size. Knowing those points is really powerful because you can get to something that's more optimal for your application. The third technique, channel reduction. So this is reducing the number of filters and channels in the net. So this is really powerful because if you used to have 256 channels and you go down to 128, or I guess maybe I could say it better as if you start out with 256 filters, you cut it to 128, and you do that for all your layers, for example, you won't just get a 2x reduction in model size, you'll actually get a 4x reduction because you multiply how many filters you have by how many channels you have. So this is very, very powerful, and this is another one where I don't have a good formula for exactly how many filters and channels you should have, but you should hunt around and look for the saturation point and then see what you can tolerate in terms of accuracy versus efficiency. But a lot of the models that I think people are using that are widely cited, you can cut down the number of channels and filters significantly without diminishing accuracy. So in this fourth one, evenly spaced downsampling, this one's a little bit of a break from making smaller models, and it's more about, given some number of parameters, how do we most effectively use them to find the right trade-off of computational efficiency and accuracy? So a design choice when designing particularly a convolutional neural net is typically the input data and the output data are different sizes, right? So the input might be an image and the output might be a vector, or the input might be an image and the output might be a semantic segmentation map that's of slightly different dimensions or smaller dimensions. So typically we have to upsample and or downsample in neural nets. So in the classification nets, we usually start with a XY grid that's the size of the image and downsample all the way down potentially to 1 by 1. So where in the net do you want to put that downsampling? Sometimes we call it downsampling max pooling. There are other techniques as well. We'll just call it pooling for simplicity. So you can put it all the way at the beginning. So you can squash the height and width of those activations down a lot at the beginning, which is kind of bad for accuracy, but doesn't use much computation. Or you could push the downsampling towards the end. So good for accuracy, bad for speed. And by the way, I'm assuming that we have this. We have some fixed number of filters and filter sizes in all the layers. We're just deciding where to downsample with respect to that. And so in our experiments, the ones that led up to SqueezeNet and ones we've done since then, something that we keep finding over and over again is that if you try to downsample as gradually as possible from beginning to end, that tends to be great for accuracy and a reasonable trade-off in terms of speed. And also stacking a bunch of downsampling layers too close together, we found can make the model diverge or can make it hard to train. So don't shock the model, just gradually downsample, and things will probably work pretty well. So back to making small models. So this is the fifth technique, depth-wise separable convolutions. It goes by different names. Some people call this group convolutions or cardinality, and sometimes it means slightly different things by each of these terms, but the basic idea is rather than having each convolution filter apply to all the channels, you have each convolution filter just apply to some of the channels. So this idea has been around for a while. Even AlexNet did this in a fairly gentle and conservative way. But what's interesting with particularly papers like MobileNets and ResNext is the discovery that you can get pretty high accuracy with neural nets even if most of the 3x3 filters in your model each only apply to one channel. So you have a separate and unique filter for each channel in your neural net layer. And the big surprise that I don't think any of us expected is that it actually doesn't kill the accuracy when you do that. Usually a fairly modest trade-off, and it's often worth it. And you could add more layers or more filters and build up to your previous accuracy level while doing this and still be coming out way ahead on how many parameters you have in your model. So that's quite exciting. Before I actually speak to this slide, let me just say, so if we've actually applied these 5 optimizations to our model so far, where we typically end up is with most of our parameters being in 1x1 convolutions. Our model is a few separable 3x3 convolutions and a boatload, admittedly a small boatload of 1x1 convolutions is what's remaining. So how do we cut down the number of parameters in those 1x1 convolutions without hurting accuracy? So one idea would be to take those 1x1s and, again, have them only apply to a few of the channels instead of all the channels. But the problem is, if you have your 3x3s and your 1x1s, let's say like in MobileNets, you're alternating between 3x3 and 1x1, and none of those filters apply to all the channels, what you end up with is a bunch of different neural nets that never talk to each other and go from beginning to end without exchanging any information. And you lose a lot of representational power that way. So an interesting approach that at least I first learned about in this paper that just came out last month called ShuffleNet is what you might call a shuffle layer. This is this kind of shockingly straightforward thing that I sort of can't believe I didn't think of myself either. Makes a lot of sense. So it's you could potentially have all the layers in your neural net only apply to a subset of the channels. So your 1x1 could be 1x1 by a third of the channels or a tenth of the channels or something. And then you do a shuffle, which I might call a transpose, so that those channels do get mixed around, so the next set of depth-wise separable convolutions have exposure to more of the channels. So I actually haven't gone into this paper in enough detail to really summarize how well it works and what the trade-offs are, but I think this general approach will be very interesting in the future. And then finally, the 7th approach and the last one, compression and distillation. So this is a whole research area in and of itself that I'll just briefly touch on. And so model distillation is one approach where instead of training directly on training data, you train to replicate the sort of probability distribution that a high accuracy, probably larger model would produce. And Jeff Hinton and that team made a lot of noise about this with a paper called Dark Knowledge, which was really interesting, but it focused more on some of the smaller data sets, and it was kind of hard to figure out how it would work in larger scale practical applications. But this paper called Mimicking Efficient Neural Nets for Object Detection really sold me on distillation. It shows significant improvements in sort of the ability of a small model to achieve high accuracy through doing this distillation approach. So that's quite exciting. And then finally, the compression side of distillation and compression. So there's a lot of research going on here. Deep compression is one of the approaches, and it unifies 3 different techniques into one system. So it deletes a good chunk of the parameters in the model. It quantizes the remaining parameters, and I think in the deep compression paper, they did the quantization pretty aggressively and used a code book, which is kind of hard to compute efficiently. But there's some more recent papers like one called Ristretto, which show that you can get at least down to 8 bits and just do linear quantization and preserve a lot of that accuracy and get a lot more efficiency. And then finally, Huffman encoding after doing the other 2. So in extreme cases, you can find as much as 30 or 40x reduction in model size through deep compression and other contemporary techniques. I would say even for really small models like SqueezeNet, we found you can do deep compression and get at least a 10x compression ratio compared to densely represented floating point numbers for the weights. So Deep neural nets have been applied to a variety of vision tasks outside of classification. A lot of my examples have been more classification-oriented. So I'll just go through these quickly as we're a little low on time. So SqueezeNet has been used for style transfer quite effectively. The not hot dog application, for those who watch Silicon Valley, they actually released a real app. One version of it used SqueezeNet, a newer one used a version of MobileNets. Chinese character recognition, 10x savings while defining the state of the art on accuracy. Semantic segmentation, this field is moving super fast and it's hard to keep up, but this ENet model has similar accuracy to the smaller version of a model called SegNet, which is quite popular, and it's 167 times smaller, which is quite exciting. And the big technique they use in this, I think, is really channel reduction. The model just doesn't have many channels. It turns out you can get pretty respectable accuracy on semantic segmentation with few channels. So the last thing, I think there's a brave new future that will be enabled by small neural nets. And there's a set of open problems to go along with that. So how small can we get? I think there's a lot of experiments going on, including the ones I've discussed here. I'd be excited to see a more theoretical underpinning as well towards what do you need in terms of representational power to solve particular problems. Algorithmic information theory may be one avenue to base that theory on. Also, can we fit deep neural nets with state-of-the-art accuracy? So, 3% top 5 error on ImageNet, for example, in like a 2-watt embedded processor's cache or less. We can kind of put neural nets everywhere if we can do that. And what can we get out of, say, a 10 kilobyte neural net? And then finally, I've mostly focused on vision because that's what I know best. But I'm interested to see which of these techniques are particularly effective in audio and text and elsewhere, and what new techniques might be needed there. And then this is pretty much the last slide. So let me make an argument that however important we think small neural networks are today, that value is going to go up significantly. So to my knowledge, there are at least 15 different startups working on brand new computer architectures targeted at specific types of neural net computations. And their objective is anywhere from a 10 to 100x improvement in computation per watt efficiency on these applications. And I think going from general purpose to special purpose processors for neural networks, there's a huge opportunity there to make things more efficient. So it's very exciting. But meanwhile, I don't see a lot of low-hanging fruit in memory. So memory is still improving. 2x improvement on the typical metrics for memory in a year would be a big deal. And so to put it all together, unless we're able to fit the neural net parameters and activations on the chip itself without a lot of off-chip communication, people will build these amazing neural net accelerators and find all their processor or all their power going to memory, which would be unfortunate. So I think the importance of small neural nets only stands to increase. So with that, I managed to get through an entire talk without talking about our startup DeepScale, which is focused on building small and efficient models, particularly for the automotive industry. And we're working with a number of big automakers that you've probably heard of on deploying these in real vehicles. And this is all very exciting, and we're always open to bringing new people in to work on this mission with us. So I'll leave it there. I think we have about 3 or 4 minutes for questions. I'll just repeat the question. It's fine.
When you say keeping them all on the chip as opposed to in RAM, what exactly does that mean? Like, does that mean it's hard-coded in when the chip's built and can't ever be changed?
I see. So the question is, what does it mean to on versus off chip, and does it have to be hard-coded in the computer architecture itself? So the way computer architectures these days tend to work is sort of a memory hierarchy. So you've got like your DRAM, L3, L2, L1 cache, and then register file. So often, at least a couple layers of that cache plus the registers will be on chip, and those are modifiable information. So it's sort of like, how can we keep everything in cache? And that may be a traditional automatically managed cache based on heuristics like most recently used and other things, or it could be the developer actually controls some of how things are stored in the cache. But yeah, it's typically SRAM or other type of technology for storing temporary variables on the chip.
Thank you for your presentation. I think you mainly talk about building new neural network architecture. However, I'm curious, that how do you think about reduce the precision of labor integration?
I see. So your question is, this talk, we mostly talked about inventing new neural net architectures, but what's the, how does that fit with reducing the bit widths or quantizing the activations or model parameters? So this deep compression work does that. There are, of course, many techniques to that. I think the two are better together, right? So we want to define the right model and compression technique. And also, we can define training protocols where from the first, pass of gradients, it's already compressed, or we can train uncompressed. And this approach actually does some training, does the compression, which includes lower bit widths of the parameters, and other approaches also do lower bit widths for activations, then actually does some more kind of fine-tuning training after that. So yeah, that's a wide open space, I think, and it's all very exciting.
So, do you think that a compressed or smaller neural network is somehow fundamentally more likely to be vulnerable to adversarial examples, or do you think that it is really making the network smaller is really independent of the vulnerability to adversarial examples? Obviously, this is incredibly important because you're talking about IoT examples, right?
Yeah. How does model size rectify with adversarial? So I think the adversarial stuff. I guess to first order, I don't know. That would be a really interesting study to do an adversarial paper where you have a variety of model sizes and see if there's any correlation. The adversarial stuff I think is a great news story and a really important area of research. But I think we should be really clear on what it means, right? It means like you can fool statistical models by tricking them with more statistics, right? You can in a different way fool humans the same way. With autonomous cars, there's like a lot of freak out about that. But I would say, well, you can also just like throw rocks at cars, right? That's like equally illegal. So, but yeah, I think the choice of model versus ability to be fooled by that. I guess a related question would be, how much of the wrong thing does the model memorize, right? And so I guess there have been studies that show that smaller models tend to be less subject to overfitting and maybe require less regularization as a result. So if those two things are correlated, that might actually be a vote in favor of small models.
So I also have a question. So rather than deciding this a priori that I'm using a 1x1 filter here and then 3x3 filter here, can you not just have 3x3 filters everywhere, but the 3x3 filters that you want to learn in beginning, you want them to be very sparse. So you put some additional group sparsity type of constraints and then let algorithm or like the data dictate what type of filters you want at each layer.
Interesting question. So there's definitely been a number of papers in that area of when to enforce the sparsity in the model, whether it's from the beginning or later on. I would say one frustrating thing about arbitrarily sparse models, let's say you have 3x3s everywhere or 10x10s everywhere or something, right, for your filter size, and you delete most of the parameters later. Well, now you've got basically a sparse matrix or sparse tensor computation problem on your hands, which is much harder to implement efficiently. So if you can kind of convince the sparsity to be in a certain shape, like 1x1s or something, at the end of the day, often it's easier to compute those efficiently because sparse matrix math tends to be a lot harder to get maximum efficiency on. But like, I think it's something that you should throw into the mix for sure.
But that is during training, right? But once you train the model, then you know where your sparsity is, and maybe while implementing it on the device, you can take care of, like you can exploit that sparsity and implement it.
It's probably true.
Dense computation there.
Yeah. A lot of options. Yeah.
Okay. I had a question. How about, have you tried something like a more adaptive setting where you use example by example, you use different routes, which convolution
What do you mean by example by example?
meaning easy versus hard, or
I see. So like, can we change the model architecture a bit based on what data we're looking at? Gosh, I mean, I think there's a lot of options there. Like in some sense, like the ResNet stuff and more recently the DenseNet stuff where it has like a lot of bypasses and things to have sort of variable depth models sort of does that, but it's not necessarily, I don't think there's an if-else statement for which kind of data you're looking at. It's more, some samples probably need fewer layers to be able to fit them, and so they might only use some of those layers. But yeah, some way to inspect the gradients and be like, oh, this is being wasted here, that's being wasted there, kind of interactively redesign the model during training. I think that would be really useful and maybe a fully or semi-automated way, but I don't think we're there yet.
Okay, so let's thank the speaker again. And